thank you very much for joining us this afternoon for our April Bite-Sized Corrosion series on stainless and beyond. My name is Vanessa Seeley-Fisher, and it's a great honor and pleasure to welcome everyone to our discussion today. Now, today is the second in our series on stainless steels, which we have titled Stainless and Beyond. And last week we had an absolutely eye-opening and fascinating discussion on duplex stainless steels. And if you missed it, please go to YouTube and watch the video. Our guest, Ken Perel, really helped me to understand some of the basics of stainless steels and where to fit duplex stainless steels into context. And today, Ken and I are going to extend this discussion on corrosion-resisting alloys and take a look at another group of metals, the nickel alloys. Now, to get us started, Ken, stainless steels, nickel alloys, they're both subgroups of corrosion-resisting alloys. How do they differ from each other?
Hey, well, yes, firstly, Vanessa, thank you for having me back. And I hope this session proves to be as informative as perhaps the last one was. So while stainless steels may contain a number of alloying elements, the primary one that makes it into a stainless steel is, of course, chromium. Yes. Of course, since it's a steel, it's an iron-based material. The point we did not really emphasize last week is the fact that stainless steels are rendered corrosion resistant by the formation of a passive layer on the metal surface. And so that's an adherent passive layer, which is very thin, and it's adherent, it can be quite tough, and it does work, and it forms in an oxidizing type environment. The corollary of that is that stainless steels are not very good in non-oxidizing environments or reducing environments. So that's the stainless steel side of things. Nickel alloys, on the other hand, or nickel on the other hand, is inherently less reactive than iron. And this can be gauged by the relative positions on the EMF or galvanic series. Nickel is more noble than iron. It's not in the same category as gold or platinum at that end of the scale, but it is more noble than iron. This infers that it may be better suited for a wide range of corrosion conditions. Over and above this, nickel has an austenitic or face-centered cube structure. And that lends itself to the addition of a wide range of different alloying elements. Now, these alloying elements can then further enhance the corrosion resistance of nickel itself over a broad range of environments. And so the nickel alloys, with the right alloying elements in them and the right application, as we'll see as we go through today, will be very useful in some very aggressive conditions.
Okay.
A useful way of displaying this principle is by means of the Y of corrosion. So it's just referred to as a Y of corrosion, but really what it does, it relates families of nickel alloys to the general nature of the corrosion environment. So on the right-hand side, we have nickel copper and nickel molybdenum alloys, which are useful in reducing environments. And on the left-hand side, it's the nickel chrome alloys, which feature in oxidizing application. Nickel chrome molybdenum alloys feature in applications which are not so clearly defined and which we term here as mixtures.
Just before we carry on too much, Ken, let's just clarify what you mean by an oxidizing environment and a reducing environment, because people can get a little confused by that.
Sure. So the corrosion process is an electrochemical one, with the metal going into solution at the anodic site, at the anode. And there's a balancing reaction at the cathodic site. In conditions that are considered reducing, the cathodic reaction is the evolution of hydrogen forms. On the other hand, in oxidizing conditions, there are several other possible cathodic reactions. And one of those, just as an example, may be the formation of water.
It looks like we can use these nickel-based alloys in many different areas. So can we chat about some of the environments where they can be useful?
Nickel alloys come into their own when the corrosion conditions are extremely severe. And this inevitably results from the combination of temperature, pressure, of course, the corrosion media itself, maybe flow conditions, most definitely from the presence of contaminants. These contaminants, well, the overall conditions might be so severe that they render stainless steels unsuitable. And particularly these contaminants are often at an unpredictable level. And that could be a bugbear for stainless steels, for selecting materials in the first place, stainless steels, nickel alloys, whatever they may be. Just to expand this point, that we know that there is a correlation, we mentioned it last week, between the chromium, molybdenum, and nitrogen in alloy, and the level of pitting or crevice corrosion resistance may be then linked to these elements by means of the formula 3.3 times the percentage of molybdenum plus 16 times the percentage of nitrogen. This is a commonly used formula for stainless steels. The one for nickel alloys might be slightly different. But ultimately, the highest value from the duplex stainless steels we spoke about last week is about 45. And for highly alloyed stainless steels, which we haven't covered in this series of talks, it can get up to about 51, 52. For nickel alloys, it can get up to 70 or 75, which means that just by being able to put more alloying elements into the material, you can enhance its localized corrosion resistance. And also, of course, as we've illustrated here, you can taper the alloy to the application so that it can be used in a wide range of environments.
We mentioned earlier and last week about the fact that chromium is useful when we're in an oxidizing environment because of that passivation layer. But now you've also said that we can use nickel in an oxidizing. Are they competing for airtime, or how can we look at these two? Are they contradictory or complementary?
Well, I think it just depends on temperatures, concentrations, and maybe in more detail. Certainly, stainless steels do need an oxidizing environment, but sometimes even what they're exposed to may be too severe. The typical oxidizing environment, and this is all in a lot of generalities, but just to provide some benchmarks to guide thinking. Typical oxidizing environments are nitric acid, chromic acid, oxidizing and acidic salts, and phosphoric acid, but it's the version of phosphoric acid that's used in the fertilizer industry, where the phosphate rock is reacted with, I think it's sulfuric acid. Another quite strongly oxidizing set of conditions is in fact concentrated sulfuric acid, above about 80% concentration. That's also quite strongly oxidizing. The three grades of nickel alloys which belong on the oxidizing side of the curve, and we haven't detailed them in the slide, you see, but one, it could be alloy 600, and that's essentially a 16% chromium alloy. You also get alloy 690, which is a 29% chromium alloy with a small amount of iron. And then the other one is alloy G35, up to about 33% chromium and a small amount of molybdenum. Just a point to note, when it comes to nickel alloys, we know most of them by their trade names. So, for example, people might know about Inconel, but that's the trade name of one manufacturer. And of course, there are others that also produce the material. Similarly, Inconel covers quite a number of different grades of metal. We could also refer to it by a UNS number, like UNSN 06600, but then I think we'd lose each other. So we've chosen to refer to it in this talk, and generally speaking, in general terms, by referring to it as alloy 600 or alloy G35, etc.
Okay, I think I'm starting to understand that where we use it, obviously, and the constituents of each of the alloys will be very much dictated by the environmental conditions. And so when we've analyzed our environment, obviously we're looking at aggressive scenarios. Once we know what the environment is doing, then we're going to start choosing the appropriate nickel alloy best suited to the conditions.
That's correct, but we shouldn't overlook the localized corrosion. And, you know, we have spoken about the role that chromium and molybdenum play. So it's not just the, let's say, oxidizing, reducing, but it's also the localized corrosion. And just on localized corrosion, last session, we spoke about stress corrosion cracking, applying to austenitic materials. And so it might be worthwhile mentioning that although nickel has an austenitic structure, the amount of nickel in the material is such that it renders the alloys immune to the classic chloride stress corrosion cracking that could affect the austenitic stainless steels.
Okay, so that's a tick for the nickel products. Now, you mentioned earlier, and we can see from the wire diagram, we've spoken now quite extensively about the oxidizing scenarios. So let's move into the reducing environments, and I'm presuming that we're now not going to have chrome, but maybe other key alloying elements that we need to consider.
You can see them on the slide. There's the nickel, the copper, and the molybdenum added to nickel. And just let's benchmark what constitute typical reducing environments. They are the halogen acids, which is typically hydrochloric or hydrofluoric acid. Those are the more common ones. You also have caustic alkalis like sodium hydroxide, alkali, and neutral salts. And importantly, dilute sulfuric acid also displays a more reducing type of behavior. Nickel-based metals that are better suited to these conditions, maybe pure nickel itself for the alkali environments, alloy 400, which is your nickel-copper alloy, or also known as Manel. And then you get the alloy B range, the nickel-molybdenum range of metals. And these latter came into being as Hastelloy B. They're useful for the hydrochloric and hydrofluoric acids.
I see sulfuric acid is going to be a challenge. If it's concentrated, it's oxidizing. If it's not concentrated, it's reducing. I think it sounds like it's just a headache, so let's move on. What about your mixtures? So I see on the slide, the middle of the wire, we're looking at a nickel, chrome, molybdenum. So now we're trying to make the best of both worlds. Is that where my sulfuric acid will sit?
That's where the action is. That's where the action is. Try and, developers have focused on trying to get alloys which cover the broadest range of conditions and still offer a good localized corrosion resistance. Firstly, we should understand that most process streams are not simply reducing or oxidizing. Secondly, many reactors are used for batches, and they might be required to operate in both sets of conditions. And thirdly, and this most importantly, as we can illustrate, very small amounts of impurities can change the behavior of the solution and can render a reducing solution oxidizing. Just to illustrate this point, the alloy B2 material has very good corrosion resistance in strongly reducing environments, typically your hydrochloric acid, but will suffer rapid corrosion if as little as 10 parts per million of ferric ions are present. So I think that's important to know. So yes, it's a good material, but it might be at risk if you can't really define the contaminants and the level of contaminants that are present. So, one might have to gravitate towards a material that is more in the center of the Y, as opposed to pinning your hopes on something that's just under the reducing column. A fourth factor to bear in mind is, again, we come back to the fact that chrome and molybdenum both have an influence on fitting and crevice corrosion resistance. So it'd be good to have both of them there. The range of alloys in the middle ground have mushroomed over the last 25 to 30 years. They may be collectively referred to as the alloy C type, alloy C families, and often one would know alloy C276 or C4 or similar materials. The initial grade, when it was first developed, had some 14% chromium and 17% molybdenum. But over the years, its composition was refined to almost equal amounts of those two elements. The grade has subsequently been developed further and tweaked by different manufacturers, by different ratios of chromium and molybdenum, maybe not equal amounts, but slightly different ratios. And with or without copper, maybe some tungsten, maybe not, or some nitrogen, maybe not. And also they've gone as far as adding a stabilizer, such as titanium or niobium. So I think overall, there's many alloys in the middle of this range. And as I said at the outset, the R&D is focused on developing an alloy that can cover the broadest range of corrosion conditions as possible. The applications for these alloys are varied, but what we might be familiar with in this country are the gold recovery industry, and scrubber systems for dirty, polluted gases that come power stations or similar type high temperature gases that are dirty and polluted and can be quite aggressive. But similarly, there's also many applications in the chemical industry, and let me say also in the mineral beneficiation industry in general, where we're looking to identify and recover metals or elements that are useful in energy storage and similar.
As you were describing the development of these mixtures, it conjured for me a picture of the kitchen, a little bit of this and a little bit of that. And I think that's probably where R&D is best suited, is people who are trying, well, what if, and try something else. And out of that comes these wonderful materials that, that you've made, these products that seem to be the magic fix all. They can work in every solution. So the question that I ask is, why would we ever not use one of these corrosion resistant alloys, these nickel-based alloys?
Well, the Americans refer to it as sticker price shock, the cost of the materials, and the instability of the pricing over time. The price and availability of nickel fluctuates, as do the other major alloying elements that get added to the alloys. This makes it difficult to manage the supply chain, upfront cost. And we all know that the upfront cost can make or break the feasibility of a project. In addition, let me say that for maintenance perspective, there never seems to be enough funds to do the repair correctly. But by the same token, this inevitably costs more in the long run. And the use of nickel alloys, whether for a project from the word go or for maintenance purposes, needs to be seen on a life cycle costing basis. And as I pointed out, that for some very demanding applications, there may be no alternatives. Stainless steels or other materials of construction may not be suitable.
I think you've got a valid point there, Ken, and it's something, and I digress from the main topic of what we're talking about, but it is a challenge, is that often when we do the research on the project, what we should be using or how we should be maintaining our equipment is one way, but unfortunately the finances get in the way. And sometimes I believe that's quite short-sighted, because if we fixed it right, we wouldn't be having to do a second fix next week or next month, but we could have our 5-year maintenance interval or whatever it is. And I think sometimes with these very high value products, and we also see it in the coatings industry, we try to save money, but that classic Afrikaans saying, when it's goedkoop is duurkoop, when it's too cheap, we're actually costing way more, because we're not being sensible in where we apply the funds, although sometimes I know CapEx and maintenance argues to the originator of the funds.
One other thing that I've noticed is with new projects, particularly in the minerals recovery industry for energy storage, companies have wanted to be the first mover. And so as a result of that, they want to bring the plants online as quickly as possible. And, the costing and all that kind of, and development work kind of has to wait. that happens too.
And I think the other thing that we need to take into account, and we all need to take cognizance of, is these super duper materials are wonderful to consider, but we always need to very carefully consider, the trace element contaminants. For example, with that hydrochloric example you gave, we do need to look at what could go wrong before we choose the material, because you're spending so much money. And you can't afford to have not done the necessary research. And that also comes back to your comment about wanting to be the first on the block. Sometimes we're not going to be the first, but we might be the one who lasts longer if we've done the right R&D. Wow, Ken, thank you. This has really been so interesting. And I don't know if you've got any other sort of closing comments in this regard related to these high nickel corrosion resistant materials.
Well, I think it's only fair just to give a few words of caution. And I think that we're dealing with materials which are high unit cost materials. And so I think you need to factor in a few things when considering using them. Firstly, don't look to select an alloy based just on textbook research or internet research. Certainly you can narrow down your range of what you want to consider. But try and do your own testing and evaluation in as realistic conditions as possible. And I think the question of the contaminants in hydrochloric acid illustrated very, very dramatically. Be aware that nickel alloys work harden extremely rapidly. And while that doesn't affect general fabrication, it does impact on anything that might need to be machined. So if there's any components that need to be machined and you're going to be doing the machining, I would urge you to just plan to do a sample before you do the first one. Because at the end of the day, you don't really get a second chance to remachine something that's work hardened. It has to be fully solution annealed, and only then can you continue. And again, just another word of caution, particularly if we tend to think of these materials in the same way as we do stainless steels. I think there's often a general rule of thumb out there for stainless steels. You've got to end off fabrication and welding with pickling and passivating. With these materials, just bear in mind that pickling and passivating may not apply. What do I mean? Well, we know that to passivate stainless steel, one of the things you can use is nitric acid. So now, if you're using nitric acid on a material that is really designed for reducing conditions, in other words, your nickel copper or your nickel molybdenum alloy, you're exposing it to something that's going to corrode it. You're not going to passivate it. You're actually going to corrode it. And we've heard of instances of that happening as well. So those are just words of caution. Perhaps another one is just to say, maybe not as words of caution, but these materials can be welded with stick electrodes, which is not applicable to something like titanium, which has to be welded under an inert gas environment. So these materials are perhaps a little bit more user-friendly than the refractory material. Finally, just to say that what I have presented is a simplification to aid in understanding, for those who may be not familiar with what in its own right could be a complex topic. Thank you.
Yeah, thank you for the caution, and I think it's well heard and definitely agreed. But I think you've really helped to shine a light on something that many of us don't know very much about, open our eyes a little bit, and we now have some more information and can go looking. And I really appreciate your willingness to share your knowledge so simply. It's incredibly helpful, and I really value that. So thank you. Ken's company, multialloys.co.za, have some incredibly useful little booklets on many of the specialty steels and specialty materials that both have been mentioned here and many others. So you can go and refer to those. I have found them incredibly helpful. So now as we close off, I'd like to say keep in touch with us via Instagram, on our LinkedIn page, via email. We love being in touch with you all and look forward to seeing you again at our next Bite-Sized Corrosion. Have a wonderful afternoon and thank you, everyone.